This video will be talking about uniform circular motion versus non-uniform circular motion, and talking about the different components of acceleration that we have with non-uniform circular motion. The radial component of acceleration, which has already been talked about with circular motion in general, as well as a tangential component of linear acceleration. And we're going to relate that tangential component of the acceleration to a new quantity called angular acceleration, which is related to how quickly angular velocity changes. Previously, when we talked about something moving in a circle, we talked about uniform circular motion. We talked about something that was moving at a constant speed around a circle. That's what uniform circular motion means. Non-uniform circular motion is when something is moving in a circle, but the speed is changing. When we have uniform circular motion, remember that that object is still accelerating. The direction of motion is changing, and so there is acceleration. And we talked about the acceleration being towards the center of the circle. The name that we gave to that was the centripetal acceleration. Centripetal means towards the center of the circle. Another name for it is the radial acceleration, the component of the acceleration along the radius. And that radial component of the acceleration, that centripetal acceleration, we get from the speed squared divided by the radius. For uniform circular motion, that speed is staying constant, so the magnitude of that radial acceleration is also staying constant. In the previous rotation video, we said that the speed, v, equals r times the angular speed, omega. There was a relationship between the linear speed and the angular speed. Using that relationship, that v equals r omega, we can see that the centripetal acceleration, or the radial component of the acceleration, can also be written in terms of the angular speed instead of the linear speed. The centripetal acceleration is v squared over r. V is r times omega, so we have r times omega, quantity squared, divided by r. So it's r squared omega squared over r. One of the r's divides out, so we're left with r times omega squared. One thing to be careful on as you're looking at rotation is the difference between position and angular position, speed or velocity and angular speed or angular velocity, acceleration or angular acceleration. If we're talking about the rotational quantity, it will specifically say angular position, angular displacement, angular speed, or rotational speed, angular acceleration. The symbols that we use for those angular quantities or those rotational quantities in our equations will be Greek letters. Theta for position, omega for the angular speed or angular velocity, and we're going to see it will be the Greek letter alpha for angular acceleration. When we have non-uniform circular motion, when the speed is changing as it moves around a circle, then the magnitude of that centripetal acceleration is going to change because the speed is changing. And there's also another component to the acceleration. There must also be a component of the acceleration that's tangent to the circle. It's the tangential acceleration. That tangential acceleration is a linear acceleration. It's the acceleration tangent to the circular path that the object is moving along. That tangential acceleration is going to be related to angular acceleration. That tangential acceleration, we will see, is r times the angular acceleration. And if there's a radial component to the acceleration, which there is for all circular motion, and there's also a tangential component to the acceleration because it's non-uniform circular motion, then the net acceleration, the overall acceleration, will not just be along the radius. We'll have to add the two components together, which we're going to see in the next slide. So like we said on the last slide, uniform circular motion, that's when the tangential speed is constant. The velocity is tangent to the circular path, and that velocity we refer to as the tangential velocity or the tangential speed, if we're just talking about how big that velocity is. In uniform circular motion, the magnitude of the tangential velocity, which is the tangential speed, is constant. And so the radial acceleration or the centripetal acceleration is constant. So that radial acceleration or the centripetal acceleration is v squared over r And on the last slide, we showed that that's equivalent to r times omega squared. If the speed is not constant, that also means that the angular velocity is not constant. The tangential speed equals r times the angular speed omega. So if the speed is changing, if r is staying the same, then omega is changing. And so if we have non-uniform circular motion, the speed is changing, but that also means the angular velocity is changing. And so for non-uniform circular motion, there will be a component to the acceleration tangent to the circle, as well as a radial component to the acceleration. In this picture, we have something undergoing non-uniform circular motion. There's a component to the acceleration in towards the center of the circle. That's what we referred to before as our centripetal acceleration, but that's the radial component of our acceleration. We also have a tangential component to the acceleration. There's a component to the acceleration that's tangent to the circle. And here, this would be causing the speed to increase. If the tangential acceleration is in the same direction as the velocity, that would be something that's speeding up. If the tangential acceleration is opposite the direction of the velocity, that would be something that slows down. But it's that tangential component of the acceleration that causes the tangential speed to change. The net acceleration, the overall acceleration, would be the sum of these two components. We have a radial component and we have a tangential component. And so the overall acceleration, the total acceleration, we have to use the Pythagorean theorem. It's the radial component squared plus the tangential component squared, square root, to get this hypotenuse. So we have to add those two components. Those two components, by definition, are perpendicular to each other. A tangent line to a circle is perpendicular to the radius of the circle. So for non-uniform circular motion, the acceleration is more complex. It has a radial component, just like all circular motion does, but it also has a tangential component. And so the net acceleration, the overall acceleration, you have to add those two components together. The tangential component of the acceleration is related to how quickly the tangential velocity is changing. That tangential acceleration is dv dt, the rate of change of the tangential velocity. V is r times omega, r times the angular velocity. So the derivative of V is the derivative of r omega, so that's r times d omega dt. It's the rate of change of the angular velocity. And we're going to see that that rate of change of the angular velocity is what we define as the angular acceleration. And something that we talked about with one-dimensional motion, if the linear acceleration is in the same direction as the velocity, the object is speeding up. So here, if the tangential component of the acceleration is in the same direction as the tangential velocity, the object is speeding up as it moves around the circle. And if the tangential component of the acceleration is in the opposite direction of the tangential velocity, that object is going to be slowing down. If something is undergoing non-uniform circular motion, this means that the net force will not just be directly towards the center of the circle. There will be a component to the net force that's towards the center of the circle, but there will also be a component of the net force that's tangent to the circle, and the overall direction of the net force will be in the overall direction of the acceleration. To understand that a little bit better, on these next two slides, we're going to look at something that's moving around a vertical circle, and we're going to look at the forces and the acceleration at some of the points on a circle that we haven't looked at before. When we did vertical circles previously, we looked at the top of the circle or the bottom of the circle. Those were parts where it was moving pretty much horizontally, and all of the forces that were acting were either towards the center of the circle or away from the center of the circle. Now we can look at what happens on the sides of the vertical circle. Those are parts where it's non-uniform circular motion. The speed is changing as it rolls up the loop. And so in this first slide, we're going to look at this ball that's rolling around this vertical circle, and it's at the 3 o'clock position. And when it's at that position, there are two forces acting on the ball. There's the force of gravity acting straight down, and there's the force of the track that's pushing to the left. Those two forces are perpendicular to each other. The force of the track is in towards the center of the circle. It's that force of the track that's responsible for changing the direction of motion of the ball. But that force of gravity is not towards the center of the circle. It's not away from the center of the circle. That force of gravity is tangent to the circle. And so as we look at this, it's a little bit more complicated. than our uniform circular motion problems that we did. The centripetal force is the component of the net force towards the center of the circle. For uniform circular motion, that component is the overall net force. We only had forces acting towards or away from the center of the circle. But for non-uniform circular motion, that centripetal force is only one of the components of the net force. It's the component that causes the centripetal acceleration, which is only a component of the overall acceleration. In this problem, the only force that's acting towards the center of the circle is the force of the track. So the force of the track is that net force towards the center of the circle. It's the component of the net force towards the center of the circle. And so that net force towards the center of the circle is going to cause the component of the acceleration towards the center of the circle, that centripetal acceleration or that radial acceleration. The radial acceleration is v squared over r, and that acceleration is going to be the force of the track divided by m. The tangential acceleration is going to be the force that's tangent to the circle, which is the force of gravity, mg, divided by m. So the tangential component of the acceleration is g, free fall acceleration. And so the total acceleration that the object would have at this 3 o'clock position, it would have this radial component that we would get from v squared over r. We would probably use conservation of energy to figure out what the speed is when it's at that 3 o'clock position. And so this radial component would be the speed squared divided by the radius. This tangential component of the acceleration would be the free fall acceleration, g. And so the total acceleration would be the radial component squared plus the tangential component squared, square root. So it would be the square root of v squared over r, quantity squared, plus g squared. Again, this centripetal acceleration, this radial component to the acceleration, is not the overall acceleration. If you're asked what is the acceleration at this position, you need to find both of these components and add them together. In this problem, one of the forces was towards the center of the circle, and one of the forces was tangent to the circle. But at some other points on the circle, it's even a little bit more complex. So let's look at this ball when it's partway up the loop at about the 4 o'clock position. There are still two forces acting on the ball at this location. There's the force of gravity, which acts straight down, mg, and there's the force of the track, which is pushing perpendicular to the track at that point. If I zoom in on this looks like an inclined plane, and so we can talk about the component of the weight that's perpendicular to the track and the component of the weight that's parallel to the track. To be able to calculate those components, we would need to describe where this is at on the loop in terms of the angle that the object makes, either with the vertical or with the horizontal. It's easiest to talk about this angle with the vertical. So if we draw an imaginary line from the ball to the center of the circle, the angle between that imaginary line and straight down, if I call that theta, that's the same as this angle between the force of gravity and this perpendicular component of the weight. Often we might be given the angle relative to a horizontal line. And so if we do that, that is this angle in the picture. It's the angle between the weight and this parallel component. Again, that's not as easy to see, but if we're writing it in terms of that angle, then the side that's opposite that angle theta 2 is that perpendicular component, and the side that's adjacent to theta 2 is that parallel component of the weight. But again, those two angles, theta and theta 2, form a 90-degree angle, and so if you know one angle, you know the other angle, and so whichever one is easier for you to see in the diagram, that's what you would use. So the reason that we have to do that is because we need to look at the forces that are tangent to the circle, and we need to look at the forces that are along the radius of the circle. The force of the track is along the radius of the circle. This perpendicular component of the weight is also along the radius of the circle, away from the center of the circle. This parallel component of the weight, the component of the weight that's parallel to the track right there, that's also the tangential component of the weight. That's the component of the force of gravity that's tangent to the circle. And so the centripetal force, that would be the net force towards the center of the circle, We make towards the center of the circle positive, so we have the force of the track in towards the center of the circle, so it's positive, and we have this component of the weight, mg sine theta 2, in terms of this angle with the horizontal. So mg sine theta 2 is the component of the weight that's away from the center of the circle. And so that force that's towards the center of the circle minus the force that's away from the center of the circle has to equal mv squared over r. That component of the net force along the radial direction is the force of the track minus the component of the force of gravity perpendicular to the loop. The tangential component of the net force, the component of the net force that's tangent to the circle, would be this component of the force of gravity parallel to the loop, this mg cosine theta 2. If we were trying to solve for the force of the track at this location, we would use conservation of energy to find what the speed is at this location, and we would look at this equation to relate that force of the track to the speed. And the force of the track only comes up in this centripetal equation, in this radial equation. The force of the track is perpendicular to the track itself. There's no component of the force of the track that's tangent or parallel to the track. Finally, just going over angular acceleration. Angular acceleration is how quickly the angular velocity is changing. So the average angular acceleration is delta omega over delta t. It's the change in angular velocity divided by the time interval. Just like average acceleration is delta v over delta t. Again, we have these linear equations, and then this is the rotational analog. This is the equation for rotational motion that's similar to our previous equation. To go from average acceleration to instantaneous acceleration, we took the limit as delta t went to 0. And so to go from average angular acceleration to instantaneous angular acceleration, that we look at the limit as delta t goes to 0 of this average angular acceleration equation, which becomes d omega dt. The instantaneous angular acceleration is the rate of change of the angular velocity. Alpha is d omega over dt. So over these last two videos, we've gone over relating position to angular position, displacement to angular displacement, velocity to angular velocity, and acceleration to angular acceleration. We've seen that the form of the equations is the same. Displacement is change in position. Angular displacement is change in angular position. Average velocity is displacement divided by time. Average angular velocity was angular displacement divided by time. Instantaneous velocity was dx dt, the derivative of position with respect to time. Instantaneous angular velocity, omega, is the derivative of the angular position theta with respect to time. So omega is d theta dt. Average acceleration is delta v over delta t. Average angular acceleration is delta omega over delta t. Instantaneous acceleration is dv dt. Instantaneous angular acceleration is d omega dt. We see that it's the same relationship, just with the rotational quantities. In the next video, we're going to take and go a step farther and start to look at the kinematic ideas with rotational quantities.